Well, hello everybody and welcome to this fifth lecture on thermodynamics. So what we'll cover today is finishing up some conversation about the second law of thermodynamics and also looking at relating our thermodynamics considerations about spontaneity with chemical equilibrium. And that's really where physical chemistry will continue in the second semester with the lecture course on chemical equilibrium. Alright, so the last time we had talked about spontaneity, and this is a slide from the last lecture where we talked about a spontaneous process being one that has a natural tendency to occur. And entropy is quite a misunderstood concept, I would say, and really what I would like to get across is this idea of entropy being considerations of how energy is distributed. So there is no change in energy when we're talking about entropy change, but we're just talking about the distribution of available energy and how it can be distributed among lots of states of equal energy. So in very casual language, we tend to talk about this about being disorder, in other words, things being more randomized. But what we really mean is the distribution of energy has more possibilities to distribute. So in simple terms, we could think about this as a molecule that's in a solid state. It'll have a very limited number of energy states available to it for the energy to be distributed. So therefore, the extent to which energy can distribute will be quite small. Whereas when that molecule is in the gaseous state, as a gas, well, it'll have lots more translational energy states available to it, for example. As a molecule, it'll have more energy, so therefore that energy will be able to be distributed across many more states. So this idea of entropy is really about distribution of energy. And we talked about spontaneous processes being ones where there is a natural tendency for that distribution of energy to increase. So when we talk about in casual language where we shuffle cards and they get more disordered, what we mean, what that's trying to sort of be an analogy for, is that there's a natural tendency for energy to distribute as widely as possible. Okay, so a spontaneous process then is one where delta S is positive. The change in entropy is positive. We are increasing the distribution possibilities of energy. And one word about the word spontaneity. Spontaneity has this sense that it's sort of there's an implied meaning about this sort of suddenness or click. But in thermodynamics, remember what we're interested in is what is the difference between start and end, this energetic difference. We do not say anything in thermodynamics about the speed of reactions. So spontaneous processes could be instantaneous, but they could take millions of years. So in thermodynamics, we have no indication about the speed of reactions. That's kinetics. That depends on the activation energy, the height of the barrier that molecules have to go over to initiate a chemical reaction. So that this note here in the bottom right-hand corner, spontaneity says nothing about the speed of a process, just that it has a natural tendency to occur. So what are spontaneous processes? Well, obviously we can think about, for example, here if we have two chambers separated by a tap, and we put a gas in one chamber and the other one is evacuated. Well, obviously when we open this tap, there's a natural tendency for the molecules in this chamber B to spread out and fill up A until the distribution of gas molecules is essentially constant throughout this entire system. So there's a natural tendency for that gas to diffuse or to mix and go into chamber A. What's happening here is we are just essentially making many more translational possibilities available to that gas molecule. So we're maximizing the distribution of energy as that gas distributes across the entire system. So obviously the forward process here, the mixing of gases until the pressure is equal, is a spontaneous process and will happen pretty much instantaneously. The reverse process is not spontaneous. We would never be in a situation where all of the gas molecules in this chamber A would flow over to B and leave a vacuum in A. Similarly, in this room that I am sitting in now, combination of nitrogen, oxygen and so on, we would never have a situation where all the nitrogen would pile up on one side of the room and all of the oxygen would pile up on the other. This distribution of energy, this drive towards spontaneous processes, means that things tend to become more disordered, which is where this very casual link between disorder and entropy comes from. So the key thing here is that this is not a process requiring energy. In other words, this spontaneous process does not require energy, and this is why thinking about spontaneity is important in thermodynamic considerations. Another thing about spontaneous processes is that obviously that they are dependent on temperature. Ice will melt into water at temperatures above 0 degrees Celsius, but will not be spontaneous below 0 degrees Celsius. There simply won't be enough energy to drive that process forward. And similarly, water will only freeze at temperatures below 0 degrees. So when we think about spontaneity, there's a temperature relationship. All right, so all of this brings us to the second law of thermodynamics. And that's essentially summarizing what we have just been talking about. Spontaneous processes are those that increase the total entropy of the universe. So there is this, second law is a really crucial underlying fundamental law of the universe, and it's saying that things will constantly drive forward so that we are continually maximizing the distribution of energy. And again, in casual language, when we talk about entropy and disorder and so on, in general parlance, we can say that the second law of thermodynamics essentially says we are continually getting more disordered, things are continually getting more chaotic, or things are continually getting worse, which in 2020 COVID times is certainly the feeling at the moment. And for this reason, the second law of thermodynamics actually is a little bit, is sort of controversial among, for example, fundamental religious groups, because they obviously, fundamental beliefs will lead people towards thinking that things are going to get better in the end and not in the worse and so on. So if you have a bit of fun on Google, you can find out some of those crazier thoughts that are out there about the second law of thermodynamics. And this essentially comes from Clausius, who essentially, there are many variations of the second law, so if you've studied physics, you'll probably get another variation, but essentially they all say the same thing. Clausius talked about the energy of the universe being constant, whereas the entropy continues towards a maximum. There is some kind of drive, this underlying drive towards increasing distributions of energies. So why is this important in thermodynamics? Well, it's important because so far we've been talking about reaction feasibility in terms of energy transformation. We've been talking about, will a reaction go downhill or uphill energetically? Is it endothermic or exothermic? Whereas now there's this second consideration, this natural drive to push things forward if it means a distribution, an increase in the distribution of energy or an increase in the entropy of the universe. This relationship between entropy and energy, and thinking about that idea of entropy being dependent on temperature, means that we can draw together the second law of thermodynamics into this pretty simple mathematical statement that says the entropy change of our observation will depend on the amount of heat that we provide to a system. Okay, so this Q value here is the heat that we've been talking about in earlier lectures. It's labelled as Q reversible here just because of the way that this expression has been derived. This reversible means that heat is added infinitesimally in very, very small amounts, so much so that if we were to reduce the amount at which we add heat by, it would be actually heat in the other direction. We don't need to worry about that at this stage. But you'll just see this notation in textbooks, Q reversible. At the moment, this is just the amount of heat that we add to our system. And the temperature is present because it's taken into account the level of disorder in the system already. Obviously, as we provide more energy to a system, well, then it's going to be able to distribute that energy across more states. We're going to make more states thermally accessible. depending on what the temperature is. So as we add heat, obviously we're going to be adding energy to a system, so we're going to be increasing the probability and the possibilities of the distribution of that energy. Okay, so this is all looking very nice. We've been thinking now about chemical reactions and thinking about them energetically. So we had our whole discussion about enthalpy, and now we're bringing in the second consideration and thinking about entropy and the forwardness of chemical reactions depending on entropy. But some problems emerge in terms of common observances. So for example, when you get into the lab, you'll obviously be making chemical substances, and very often you will have a substance in a solution and you will want that to crystallize. So you get your glass rod and you scrape the bottom of the glass to try and initiate a crystallization process, and hopefully you'll get crystals. But if we think about it, and again I'm using the common parlance here of just disorder, but we understand now that this means essentially distribution of energy. But here we would be going from ions in a solution to ions in a very highly ordered solid. So the energy distribution possibilities are drastically reducing. So clearly here the entropy of this process, the entropy of crystallization is negative. We are not increasing the disorder of the system. We're not increasing the possibilities of entropy of energy distribution. And the way we can sort of rationalize this is to remember that the entropy change that we need to consider, according to the second law of thermodynamics, is the total entropy of the universe. Whereas what I've been talking about in my crystallization here is the entropy of the system. So yes, we may have situations, and we very often do have situations, where the entropy change of the system decreases, but that in turn, if it's a process that's feasible, according to the second law, that in turn must mean that the entropy changes of the surroundings increase to a larger extent, so that the overall entropy change of the universe, system plus surroundings, increases. Okay, so remember the second law of thermodynamics talks about this entropy change of the universe. So this is a bit of a pain, because now we need to think about, well, what is the entropy change of the system? What is the entropy change of the surroundings? Okay, so obviously there will be entropy change of the surroundings here. This is an open system. It can interact with the surroundings. So we need to think about these two separately and then worry about the entropy change of the universe so that we can use the second law of thermodynamics. So where are we? Well, we are in a situation where the enthalpy gives us a sense of the energy demands of a reaction, whether it's exothermic or endothermic, and entropy gives us a sense of the extent of energy distribution or changes in disorder of a chemical reaction. And we set out on this course wanting to answer the question, how can we tell whether a chemical reaction can proceed? And we clearly need to bring together both of these concepts. So this was work done by Gibbs, and this is essentially trying to pull together these two parallel considerations about whether a reaction can proceed. So we know from our discussion that the entropy change will be the entropy change of a system plus the entropy change in the surroundings. Well, let's have a look at the entropy change of the surroundings, because obviously this is a little bit difficult to conceptualize. So if we have some reaction, and that reaction is endothermic, for example, it's going to affect the surroundings. If it's endothermic, it's going to pull in heat from the surroundings. So from the perspective of the surroundings, it's exothermic. It's pushing heat away from the surroundings and into the system. So therefore, the enthalpy of our surroundings change, the enthalpy change in our surroundings will be the negative of the enthalpy change in our system. If I am heating up a system, well, that heat is being taken from the surroundings, so the amount of energy in the surroundings is decreasing. So that means then we can use the second law of thermodynamics and say, well, the entropy change of the surroundings is equal to Q over T, and we know at constant pressure Q is equal to delta H. So therefore the entropy change of the surroundings is minus delta H over T. So this is now an expression of the entropy change in the surroundings in terms of something we know about the system, the enthalpy change in the system. Alright, so this is really useful because we now have some expression of the surroundings. It's a very difficult thing to consider because the surroundings is essentially the entire universe apart from our system. But we now have it expressed in the form of something to do with the system. And this is at constant pressure, remember, because remember Q at constant pressure is equal to delta H. If it was a constant volume, well, then this would be delta U. Right, so that means then, well, we can just start subbing things in. We can say that the entropy change in our surroundings is minus delta H over T, delta H of the system. So that means the total entropy change is equal to the entropy change in the system minus this value delta H over temperature. So if we multiply across by T, well then we get the entropy, the total entropy change times the temperature is equal to the temperature times the entropy change in the system minus delta H. So that means then this T delta S total is equal to minus delta H minus upon delta H minus T delta S. And if we call this value here, if we call this what's the Gibbs Free Energy, well then we can say that the Gibbs Free Energy change is equal to minus T delta S total. So that leaves us with the very famous expression that you all know and love, that the Gibbs Free Energy change of a reaction is equal to delta H minus T delta S. And we can see the second law says that this T delta S total value must be positive. The entropy change of the universe must be positive. So if that must be positive, well then, and it's equal to the negative of delta G, well then for a spontaneous reaction, the reaction Gibbs free energy, delta G must be negative. And the great thing about this process, if I just go back to the previous slide, is that as soon as we related this entropy change of the surroundings to something to do with the system, everything here now is to do with the system. So everything in our Gibbs free energy formula is to do with the system. So delta G is equal to delta H minus T delta S. Okay, so this OR here, this reaction Gibbs free energy, is telling us that this is for our system, the Gibbs free energy change of the system. And this is great because all we need to do now is we're well versed in calculating delta S, delta H, well versed in calculating delta S, so we can very easily calculate those numbers for the system, calculate this delta G value, determine whether it's positive or negative, and finally now we have an answer to this lecture course. Can we tell whether or not a reaction is spontaneous? Yes, we can. We calculate delta G. Okay, so this is essentially the journey we've been on in this lecture course. We started off in pretty vague terms, thinking about this y-axis in terms of potential energy, thinking about how energy transformation occurs and what that means in terms of potential energy, kinetic energy, and so on. And then we phrased it in terms of internal energy, and then related this energy change, thinking about, well, it's too difficult to conceive all the types of energy that are transforming, so let's just worry about the change in internal energy. And while we mightn't know the actual values here of products and reactants, we can easily determine the change. And then we related that to, rather than having to worry about pressure, volume, work all the time, we related that to enthalpy change and said, okay, well, we can just determine whether or not at constant pressure, whether or not a reaction is exothermic or endothermic. And then we brought in the second law of thermodynamics in this lecture and said, well, it's not only about the enthalpy considerations, it's also the entropy considerations. So now, finally, we have this final setup where we can say Gibbs free energy change gives us an indication of spontaneity. If delta G is negative, okay, our Gibbs free energy of products is lower than the Gibbs free energy of reactants, well then the reaction is spontaneous. If it's positive, in other words, this product value is higher than the reactant value, it's negative. Sorry, it's not spontaneous. So that then summarizes where we're at. We can say, well, from this formula, we can see it's going to be this competition between delta H and delta S. If we want delta G to be negative, well then we have four combinations, because delta H can be positive or negative and delta S can be positive or negative. So let's say if delta H is positive, we have an endothermic reaction. Well, I suppose our gut instinct would tell us, well, if we need to provide heat to a reaction, it's not going to be spontaneous. Whereas we can have situations where at large enough delta S values, in other words, if the second law really pushes this reaction forward, it really drives it forward, well then we will get a large enough minus T delta S value to overwhelm the enthalpy considerations to make this overall bit positive. So in situations where we have endothermic reactions, our reactions can still proceed, and it's what's called entropically driven. In other words, delta S is sort of pushing it forward, even though it needs to take in energy from the surroundings. So delta G can be negative at high temperatures once the delta S value is positive. But of course, at situations where we have an endothermic reaction and delta S is negative, or if delta S is negative, the second law of thermodynamics is not going to be driving this reaction forward, because minus by minus will be plus here. So this first term will be positive, this second term will be positive. There will never be a situation where that reaction is spontaneous. That reaction will always be non-spontaneous. And then similarly, if we have an exothermic reaction, well, we have a situation where we have a negative value here. So again, from just considering the first law and energy differences, if we have a situation where a reaction is proceeding and giving off energy, common sense would tell us that it tends to be a spontaneous reaction. So we can see here that will always be spontaneous when delta S is positive. So in other words, both of these are lining up to give us a negative value. There may be very unusual situations where the delta S being negative would push this value to be more positive than the negative delta H, and we may find that at very high temperatures this reaction is non-spontaneous. But in general terms, if we have exothermic reactions, it's very unusual for a reaction not to be spontaneous. Okay, so this is our summary of the three laws of thermodynamics. First law really talked about internal energy and allowed us to think about energy transformation in terms of heat and work. Second law really then said, well, as well as energy considerations, we need to think about how that energy is being distributed. Entropy considerations, reactions being spontaneous, where the entropy change of the universe increases. And the third law, if you remember, we just said that there's this essentially allows us to give a baseline for entropy calculations. Right, so we can use this kind of information to very easily determine reaction spontaneity. So our spontaneity criterion essentially said, well, if we can work out this delta G value, delta G is equal to delta H minus T delta S, and determine whether or not spontaneous, whether or not it's negative, that will tell us if it's spontaneous. So for example, here we can use standard values for delta G and work out using, for example, the Gibbs Free Energy of formation values of reactants and products. We could just take products minus reactants and work out our delta G value and find out here it's very highly positive. So clearly this is not going to be a spontaneous reaction under the conditions. And this is where it's very important to be careful using the notation. So we have said that our general consideration about spontaneity is delta G. So if delta G is negative, well then the reaction will be spontaneous. But this does not presume any conditions. So you just need to be careful when you're doing these calculations, because most often we have standard values. We use these standard values and they refer to single specific chemical states where everything is in their standard state. And we saw that we can easily calculate delta H, we can easily calculate delta S, but that will give us delta G under standard states. So we need a way of relating these standard states to our actual conditions, and I'll come back to that in a moment. But nevertheless, we can do lots of simple calculations. So for example, here we have delta F values, enthalpy of formation. So that will allow us determine the enthalpy of reaction. So we can easily determine the enthalpy of reaction. Knowing from the previous slide our delta G value, we can work out the entropy of a reaction, and I can show you a way of estimating the minimum temperature that this reaction will proceed. So let's just go through this quickly. So if we know our enthalpies of formation, well, we know from before that the enthalpy of reaction will be the enthalpy of formation of products minus the enthalpy of formation of reactants. So this gives us this very large endothermic reaction. So So we can see where a large positive Gibbs free energy is coming from. The entropy of reaction, well, we calculated on the previous slide that the Gibbs free energy was 130 kilojoules. So if I rearrange my Gibbs formula, that'll give me delta S as delta H minus delta G over T. So that'll give me an entropy value of 162 joules per Kelvin per mole. Okay, and that's, again, if we look at our reaction, we're forming one gas. So if we remember standard entropies, standard molar entropies, forming one gas, well, that tends to be in the hundreds of joules per Kelvin per mole range. So that value makes sense. And this is a little bit of hope. We have a positive delta S here. So even though we have a large positive enthalpy of reaction, this positive delta S means that if we ramp up the temperature, we can make this reaction spontaneous. We can force it to proceed. And we can do that calculation because we can say, well, if we know for a spontaneous reaction that delta G is negative, well, delta G is delta H minus T delta S, so if that has to be negative, well, rearranging that gives us temperature is greater than delta H over delta S will be the minimum temperature for a reaction to proceed. So to work that out, we can put in our enthalpy and entropy values, and we get a value of about 1100 Kelvin. The caveat here, of course, is that this is an estimate because, of course, as we change temperature, we know from Kirchhoff's law, for example, that the enthalpy of reaction will change and the entropy of reaction will change. So we would need to correct those to get the actual value here. Okay, but this issue about notation. So far we've been talking about using standard values to calculate delta G, but our derivation of Gibbs free energy, it doesn't presume any standard condition. So clearly we need to be able to relate these. So what I'm saying is, in the calcium carbonate example, we worked out a delta G value of 130 kilojoules per mole. That means unless we move very far away from standard conditions, we can assume that this is not a spontaneous reaction. And similarly here we have a hugely spontaneous reaction. Hydrogen plus oxygen in the presence of a spark will form water. Very, very large exothermic reaction. So again, unless we move away from extreme to extreme conditions where we are not very close to standard conditions, we can assume that that reaction will be spontaneous. So in other words, even though I'm saying standard values are limiting in that it only tells us about the standard condition, and we have very large positive or very large negative situations, they will give us a good indication of spontaneity of a reaction. The difficulty emerges when we have delta or G values as under standard conditions that are around zero, because obviously here the conditions will determine whether or not this, under non-standard conditions, whether or not this reaction will be spontaneous or negative. So spontaneous or not. So we need a way of relating delta G to delta G under standard conditions. So if we think about some chemical reaction, we think about a reaction where we are changing the conditions. So we may have a chemical reaction where we have reactants going to products. Well, we can determine what's called the extent of the reaction, in other words, how far this reaction has proceeded at any stage, by thinking about the reaction quotient Q, thinking about our concentration of products, thinking about our concentration of reactants. And we can say, well, obviously as we're forming our products, well, the concentration of reactants will decrease, the concentration of our products will increase, and energetically this reaction, if it's proceeding at all, will proceed, and then it'll reach some point, equilibrium point, at which it's no longer going to proceed, and it won't go any further than that. So the extent of a chemical reaction obviously depends on equilibrium point, in other words, at what stage it reaches equilibrium. So at any stage in this reaction, if we are here in this reaction, for example, or we are here, or we are here, well, if we haven't reached our equilibrium point, according to our reaction quotient, well, then that reaction will still be spontaneous. If we push the system past this equilibrium point, well, then the reverse reaction will be spontaneous. So in other words, the point at which a reaction reaches equilibrium will be very important in thinking about reaction spontaneity. So if we allow a reaction to proceed and it reaches equilibrium, well, clearly we have this situation where reaction can and will go from reactants to products. So an equilibrium reaction, as you'll pick up in the next lecture course in semester 2, allows us essentially to say, well, these are reactants that are constantly reacting and forming products. Some of those products will be dissociating and going back to reactants. So we have this very dynamic situation where products and reactants are continually forming and disintegrating. But the concentrations at which they are at will begin to level off at equilibrium. So at equilibrium, this reaction is still furiously going backwards and forwards, but the actual concentrations are staying the same because the rate of the forward and reverse reactions are the same. So we use this double-headed arrow here, this equilibrium symbol, to indicate that we have an equilibrium mixture. And at equilibrium, we have a very special consideration of Q, the reaction quotient, because this is the one point in the chemical reaction where the concentrations of products and reactants essentially settle. They essentially stabilize and form a constant concentration. And again, that is not to say that this reaction doesn't continue to go forward and backwards. It does. Both these reactions are still happening at equilibrium, still moving. Lots of molecules are still reacting and forming products. Lots of products are still reverting to go back and form reactants. But because of those rates being the same in both directions, for us as an observer looking at it, the concentrations stay the same. These equilibrium concentrations are the concentrations at this point where the rate of forward and reverse reactions are equal. So we call this very special condition of reaction quotient the equilibrium constant, or the equilibrium state, and we tend not to write in these equilibrium concentrations, but I'm just doing that here just to emphasize that this is a one-time only situation where these concentrations are very particular value rather than the generic values we're writing for Q. So that means then we can look at a chemical reaction and we can say at any particular point whether a reaction will be spontaneous in the forward direction or the reverse direction. So if Q is less than K, well then we want more products to form to increase the value of Q so that it reaches the equilibrium value. If Q is greater than K, in other words we have somehow pushed the reaction to form more products than equilibrium, well then the concentration of products will decrease, so the reverse reaction is spontaneous. And at Q is equal to K, the reaction isn't going to change concentration in any direction, so we say it is at equilibrium. So all of this allows us now to relate delta G and delta G under standard conditions. There's clearly a link between the Gibbs Free Energy and the standard Gibbs Free Energy by thinking about where the system is at in terms of its overall reaction profile. So we can say that as we deviate from standard conditions, as we deviate from this very particular state or very particular pressure or whatever, and go towards reaction conditions, well, that extent of deviation is quantified by the extent to which products and reactants differ in concentration from the standard conditions. And because we said at equilibrium delta G is equal to 0, and at equilibrium the reaction quotient is equal to K, well, if we substitute both of these values into our expression here, we end up with this expression. The standard conditions delta G value is equal to minus RT ln K. And this is an equation you've probably come across before, but I want to emphasize how valuable and how important this equation is, because it allows us relate two things. It allows us relate standard values, things that we are very easily able to calculate from tabulated data. So we've seen all the enthalpies of formation, we've seen all the standard molar entropies, we can see how easy it is to calculate delta G. So that is all of our thermodynamics course wrapped up in that little value. And this K value is experimental. It's saying what is happening in our system, in our lab, that these are non-standard conditions or whatever it is, whatever our particular setup is experimentally. And this Van 't Hoff isotherm is relating these two concepts. It's bringing together all of our thermodynamic knowledge and relating it to something experimental. We can very easily calculate equilibrium constant in the lab, and that will give us thermodynamic information, or we can very easily determine thermodynamic information from standard tables and relate that to some observation we may see in the lab. It's a very powerful relationship. And Equilibria, the course in semester 2, will pick that up. Okay, so we can easily use this. We can see here that at particular conditions beyond at conditions in a particular cell, for example, here we have glucose plus phosphate gives glucose 6-phosphate. Well, we can easily work out the relationship between the equilibrium constant K and hence delta G. So we can say that K will be the concentration of products, glucose 6-phosphate, divided by the concentration of reactants. So that's our experimental value. Okay, that's what we're actually observing in our system. And then we can relate that to delta G and say, well, under standard conditions, will this reaction be spontaneous? And we can see here when we do the calculation, we get a positive value, so it is not spontaneous. So relating delta G and K essentially brings all the thermodynamic course that we've been thinking about and relates it to experimental lab-based science. Okay, so in the last few lectures we've been working through this question, and I'd like you now to continue this question. So you can see here that we had calculated enthalpies of combustion and entropies and so on, and now the last part of that question is to work out the delta G value. So I'll leave that with you to work out.